Thank you. I thank the organizers for giving me the opportunity to present our results here. So I will talk about this class of semimetals that have been realized in recent times. And I'll sort of trace the line of thinking that led to this type of this type of topological semimetals. So of course, the idea of biophysics appearing in crystal is not new. It goes back to 1937. In fact, these accidental degeneracies in the band structure of crystals have been discussed for quite a while. But now the question is, if the idea is so, these ideas have been there for such a long time, then why it did not happen in real experiments? Why this type of physics was not realized? And interestingly, I found that both Weyl and this condensed matter or solid state Weyl, those two papers were written from Princeton. So, but I did not know that before I got to this topic. Okay, but I think although one can say that this paper has the topological aspect built in there, I mean it's straightforward, but then the topological aspects were in some way revived in recent times in connection to topological insulators and topological states of matter in general. And then these invariants these are not, of course, Zahid invariants in topological case. Okay, so as I said, starting from these theoretical ideas to real materials, there is a long way. I mean, you can see there are many decades how to realize that physics. So this would be in some way, outline of my talk. That in 2014 we published this paper on Fermi states in topological materials, and how that sort of ideas led to later development of this fermion physics, and also in 3 dimensions. Not only you have the semimetal, as you heard in previous talks, that you can also have a variant topological nodal line fermions. This is also realized now. I mean, we have a number of papers on that. So in some way, the overview of my talk is to describe how we figured out this experimental realization of topological semimetals and measured their topological invariants. Okay, so shortly after the Weyl paper, there 2 other groups had papers on similar topic. This one is from MIT. This is on photonic crystals. So in a photonic crystal, you don't have a fermion, so this is like a bosonic analog of Weyl. And then after that, Hao Zheng will give a talk. This is their first paper. And after these 3 papers, there are a number of maybe a dozen of papers that appeared further supporting these 3 papers. Okay, so let me acknowledge my collaborators and the funding structure. So my lab at Princeton is mostly funded by Moore Foundation and DOE, starting and a little bit of NSF. And we do a variety of things and collaborate with a number of groups. So the band calculations I will show, the material identification, typically it starts with my students at Princeton, and then we collaborate with a number of groups, notably Hsin Lin in Singapore and Raman Sankar in Northeastern, and more recently with Titus Neupert at the Princeton Theory Center. And then on the material side, we collaborate with Fangcheng Chou, Shuang Jia, Chenglong. This is Shuang Sankar played a key role in the semimetal, the ones I'll talk about, and also Raman Sankar. And the experiments are carried out in various national labs, mostly in these 3 labs, and I'll go back to this in connection with the data, more the details. Okay. So the part of the talk I'm focusing here is a collective group effort, but the BI part is led by Shuang Jia, and the nodal line part is led by Guang Bian. They're all here. Madhab was working on the Dirac semimetal. He is now running his own group at the University of Florida. He also gave very private talk, so I'll skip this part. And then Ilya, Nasser, and Hao, they're all a significant contributor to all these developments. And these new developments are built up of my first generation of students. They're all running their own groups now. Okay, so coming to the algorithm, what is the experimental development that led to the identification of topological states of matter? And this same set of ideas led to the experimental identification of the biophysics. So in most of this, almost all of this topological material, there is some sort of bulk boundary physics going on. So you have to probe the bulk. Sometimes bulk can be spin texture, but surface will definitely be spin texture. And there will be some non-trivial phase. And how to probe all of that is this methodology in the ARCUS community. We know that it's a relatively new development. ARCUS is not a new technique, but the development is relatively new in the sense that this methodology is not typically applied to study, like say high DC or nuclide and all this. So that's so with the development of topological materials, ARCUS also had to develop specific routines, subroutines of experiments. And these methodologies, since I'm not going to go over these new developments, I'm just citing these papers that we have demonstrated, and this can be found in this review article. So to summarize, the basic idea is to look at the bulk and the boundary and connect the two in energy, momentum, and spin space. And that will give you all these things, all these topological invariants. They are defined in that energy, momentum, and spin space. So you need to probe all these things. So these are the key results in topological insulators. So another thing to note is that this topological insulator is a gapped phase of matter. So you can make a distinction between a boundary mode and the bulk mode. So the boundary electron cannot enter the bulk because there is a gap barrier. So that topological classification that in a bulk boundary sense is a robust idea. Similarly, it's not the only gap topological phase of matter, of course. This is without symmetry breaking, but you could also have topological states of matter with some sort of symmetry breaking, superconductivity, for example. So then you could take a topological insulator, get the Dirac surface state superconducting in various ways, and then again in energy, momentum, and spin space, you can probe the gap structure and superconducting coherence and all of that. So that this is again the same algorithm that you probe the surface spin texture and the bulk boundary correspondence through by measuring all the degrees of freedom of the electron. Now you might think, based on this set of algorithms, that it sounds like if you close the gap, then how can you get a topological states? Because now the boundary mode is not well defined. How can something is confined on the surface if there's no gap? So if there's no gap, energy barrier to enter the bulk, then the electron will enter the bulk. So apparently, it will look like that a gapless topological state is not a robust idea. So this is the key question, and this is the non-triviality from topological insulator, topological superconductor. And I believe it also took some time for many of us to realize how to find them in material space. So this gaplessness, and this can happen in 3+1D. And the fact that it can happen in 3+1D, as I said, there's ancient literature, but the new ideas with topological insulators gave new clues to realize that. So one way to look at it is from the invariant structure. This is from Holovik's invariant structure, and then you could see that topological invariants describe these monopoles in momentum space. So how does that translate in let's say take one of these monopoles and in the bulk momentum space and project it on the surface, then that projection gives rise to the fractional Fermi surface when you consider a single surface. And such a fractional Fermi surface cannot exist in an isolated 2D system. It must exist on the boundary of a 3D system. So in this sense, this 2D electron gas is a new state of matter. You cannot realize that in 2D in an isolated way. Okay, so the early proposals in connection to all of this were actually on magnetic materials. This first proposal by this group of authors, they talked about iridates, the magnetic order, and also the previous talk, Guoqing Chang's paper is also on T breaking. Similarly, from IOP group, they predicted in 2012 that mercury cadmium selenide, also the magnetic state, these are all T breaking compounds. So when I looked at these proposals, I realized that this is not the easy experimental route to realize that. Even to this day, none of these theoretical predictions, they're perfect as a theory paper, but they did not lead to any experimental realization. So predicting some material, there are so many of those, doesn't necessarily guarantee that it will happen in experiments. It doesn't matter how nice that idea is. We have seen that here. So early on, I realized around the same time that the easiest route would be to consider I-breaking, inversion breaking systems. This inversion breaking was explicitly talked about Murakami first, and that's where I learned that part. But Murakami did not present a clean material. So then Lin, Bansil, and myself, we predicted a number of materials in this paper in 2012 that could be used, and that could be, and those materials are real. But the challenge with those materials is that the bias splitting is small, and even though it should happen in transport, it's not easy to resolve in APS. APS is a 1 millivolt probe, it's not a 10th of millivolt probe. So that set of ideas took us further, again, in connection to our earlier data on topological phase transition, how you take a band insulator and turn into a topological insulator, or the other way around. So you tune spin-orbit coupling through the lattice by changing by substituting some atom. So when you do that, then at the phase transition, when the band insulator becomes a topological insulator, you get a 3D Dirac state. And then that 3D Dirac state in some way is a parent state, and you can drive other things, other phases out of it. So if you like, you can think of that as the parent state, and we demonstrated that back in 2011 before prediction of any other 3D materials, 3D Dirac materials. So then what was our route to find from out of that Dirac state? So I suggested my student Ray to magnetize this Dirac critical point, and Madhab Neupane and Shankar, they're here to magnetize these Dirac compounds, and Suyang and Ilya to search in the database to find the analogs of this transition, this critical point in the material space, in the database space. You could find materials with similar space groups, similar spin orbit coupling in a critical state. So it turned out it's extremely difficult to reliably magnetize these things and isolate the blind point. I'm sure it will happen in transport, but to resolve in APS is a tremendous challenge. It's not resolvable. So then, what happens when you search for compounds in the database? You get hundreds of entries, right? So you can start calculating everything, but then what is the algorithm we use to find out what will actually work? So in some ways, specific to APS, it's like it's in some ways a selfish algorithm. So many of these compounds, still, I did not rule out, they could be Weyl semimetals or nodal lines and other things. There are more than 100 space groups. So how do we pick which ones we should calculate, which one we should tell our collaborators to calculate? So the number one is that you can look up, some of these materials have never been grown in a single crystal form. It's not going to work for my experiment. And there's further stringent condition that for APS to work, you have to have a material that fits. And in many of these material characterization papers you can find in the database, they already tell you whether the sample fits or not. So then with that, even though theoretically if you search, you get a huge entry, large entries, but for us, for my group particularly, I can only pick the ones that will work for APS and focus on those things. So this is the challenge. If when you do the theoretical search, you get more than 1,000 entries. And not only that, you can browse through the compounds and see that many of them have negative MR. Negative magnitude resistance doesn't imply you have valid points. I mean, it will look like chiral anomaly, but there are other ways that can happen. So transport properties do not help. It doesn't give you a unique signature how to find one. And then even if you calculate some of these things, the bulk nodes may appear in arbitrary K points. You know, even iron crystal has 5 points, right? But it's not useful. It's not a semimetal in a real sense, in a functional sense. And then you could also ask, these calculations do not tell you what is the Fermi level, right? So, and what is the cleaved surface potential? If you don't know the cleaved surface potential, you cannot match up to the details of the band structure, say that, okay, my data agrees with the band structure so much, I can conclude that this is something. But the people who do actually do this band structure calculation, they know that the surface potential is not known. For example, if you say van der Waals termination, that's not consistent with the biosemimetal, it's a 3D state. So it has to come from experiment. And how to separate surface and bulk? You could have these bulk nodes, but they could be, the surface and bulk would be nearly degenerate, like in a nodal line state. Okay, so the point I'm trying to get to, I'm giving a realistic algorithm when and how theoretical predictions actually work in experiment, because there's a long way to go. So this is, so in that search process, my students found out this process and we started to calculate these things because we already know that this is going to work. Okay, so not only that, in that same search process, it's not only we predicted tantalum arsenide flux, we also predicted a whole lot of other things. So this is, it's using the same algorithm. You can find these papers in the journal or in the archive. So, but then prediction is of course quite straightforward in realizing and proving that in experiments. So I mean the rest of my talk will focus on that. But I'll briefly review the theoretical predictions my group has made. For example, this biosemimetal, it could be it could achieve a file to insulator transition in the system. This one is a quadratic file. It's not what Hasan Kane talked about, but we could define that in this class of materials. There are other file physics beyond, and you could also have tilted file. So, for example, this system has tilted file. A number of other groups have also predicted that. So let me come back to the intuition that led us to find some of these things, and which is this algorithm is given in this paper. So what is that idea? It's similar to the Murakami transition, the phase transition he talked about when he showed our 2011 science paper. It's already implicit in there. So since we were working on topological insulators, we know how it looks when you have Fermi level in the gap. You have a Dirac circle. I mean, Dirac surface states give rise to a circle. Now imagine closing the band gap of the bulk, the topological insulator band gap at 2 points in the Bian zone. Let's say you close it there. Now immediately you will think that you lost the Z2 invariants. The Z2 invariants are not defined for the gap closed system, right? So then you would say that what is protecting these surface states? Nothing should be protecting them. In fact, I asked Charlie Kane this question, and he agreed that there's no protection mechanism for that. But then you could say, always say, make a trivial statement that, okay, maybe there is some crystal symmetry that will protect the states, right? So indeed, that can happen. But then, if that is the case, then you can also further play with the crystal symmetry. Then you consider, okay, now what happens, so these are Dirac crossing. Now what happens if I introduce inversion breaking in the crystal, or find a non-centrosymmetric analog of this crystal in the spin orbit and neutral space. And then that means, in that case, your Dirac point will split because now you broke the inversion symmetry, and we know the way Dirac spinor can be split is a Weyl spinor, right? You take two Weyl spinors and make a Dirac spinor. That's consistent with crystal symmetry, translational symmetry. So that's the algorithm to find a Weyl-semimetal, right? And then you could do further operation. You could annihilate the Weyl nodes in momentum space through other operations. So then comes the experimental algorithm. How do you prove that in ARPES? What is the idea? That we gave in 2014 in a science paper, demonstrated the fermion surface state. So this is in a theory-independent way. I don't want to believe band calculation and say, okay, my data is so much with calculation because this is a meaningless statement. Because the calculation doesn't know what is the detail of the potential. And I'll show examples by varying the detail of the potential, how much the band structure varies. And that is, so those things are useless in a functional sense. So what is the idea here? That you, if you do an ARPES scan and then do a 3D imaging of the state, you have a Fermi surface, then you say that the Fermi surface, find that the Fermi surface is not strictly surface state, it's not a resonant state, but it's somehow mixture of a 3D state only on some points, and the rest of it is 2D, and then it has a specific spin texture. So then this spin space and the 3D momentum energy space gives you a clear picture independent of any calculation of energy. So we apply these ideas to the compounds we predicted and see what happens. Okay, so, well, I reviewed that conceptually. There is also a prediction from IOP group. This paper was submitted 2 months later. But the essential ingredients agree on the topological structure that there are 24 Weyl nodes. So the basic idea is that you have two mirror planes. If you turn off spin orbit, then you get these nodal line states. And then when you turn on spin orbit, the nodal line will vaporize, condense into Weyl points. You have two pairs here. They project. So this would be ARPES-like projection. That's why this diagram appears in our theory paper, because we're thinking about ARPES projection of that. So then you have this pair projecting here, and then you have this is not in scale. These 2 points are closer. And then you have some, under certain conditions, you could have monopole-like structure there. Okay, so now I'm changing the surface potential because I don't know in calculation what is the real surface, what will actually surface data look like. So if you take a combination of surface potential, then you'll see that on this direction you have these bow tie states here. You can make them disappear, and you don't have a double line. You have a single line kind of resonant state, and then you could also have situations you have double lines. So what we do in experiment is we, after cleavage, we scan and try to see guess what is the favorable surface potential, because all these Fermi surfaces are topologically consistent. They are topologically equivalent. So the details do not matter. So I can select certain data sets from certain cleaves because the surface potential is different and find a clean system where that surface state part dominates. I don't run into resonant or other power states. So these are some of the typical data sets. For example, the surface is not fourfold. The gamma x and gamma y are not the same. In this direction, you can see that there are too many things. So we don't resolve much. So we gave up hope after trying many samples that we cannot resolve much. But for the topological proof, I just need one open Fermi arc to demonstrate one open Fermi arc. So then you can see that the y direction you have parallel lines, but the surface potential can be tuned to minimize that, because these are, in our experiment, they're more resonant line. So I want to select the gamma x line. They're not the same, you can see that. So when I take the gamma x line, then the essential idea is to consider a loop construction around that, then if and see whether there is a co-propagating state or counter-propagating state. If I have co-propagating states, that means they are chiral A states, they are spin texture, so term number 2, and then when I consider the cylinder in the APS geometry, it's coming from W2 projection. And this is, you cannot get co-propagating states in a Dirac semimetal or regular semimetal. You will always get counter-propagating state. So this is like quantum Hall, double quantum Hall gauge. So you can have you can have that in the band structure. So this is precisely the construction we did. Now you can see that this extended line is not there. If it would be there, it would show up. So in this direction, for this surface potential, this is a non-closed Fermion. Of course, when you go on this direction, it becomes more complicated. But this is gamma x direction, which is most favorable, not the gamma y direction. Of course, gamma y, resolving that in the gamma y direction is more challenging because there are like 5 other stuff. But to show that W2Y structure, the topological structure, you can see that there's nothing and then they're co-propagating. So I completely avoided calculus by changing the surface potential experimentally and I am not referring to any calculation to prove the topological structure. So as you know, just from the Dirac equation, just as Majorana is like a half electron, Weyl is also a half electron in a different way. So then you should be able to see that the 2 Weyls make a Dirac, and that you could also see that by making the bulk Fermi surface, So these are the 2 points in the bulk. There are other stuff, but that's different origin. And then you have this open, non-closed Fermi surface. We achieve that by doing low photon energy, which is surface sensitive, and then if you go to high photon energy, you see that. So this is a proof that the APS can be bulk sensitive and surface sensitive, right? So now I want to put them together. Since I'm running out of time, I want to look at their band structure down and then put them together and see what happens. So I'm putting low energy APS and high energy APS together, and we see that the Fermi arcs terminate where the bulk Fermi points, the Y nodes appear, and they coincide in momentum space. So this is the bulk boundary correspondence, and that proves the topological nature of the Y state. Okay, so then this same construction, this experimental algorithm, we then applied it to all of the vectors we predicted, and then we discovered one after another. But the key thing is not comparison with calculation. Develop this chiral state algorithm and do this momentum space construction and find the surface potential where that line connection is minimized. And you need to find only one open non-closed Fermi surface. That's good enough. You don't have to image everything. Of course, you can try to image everything, so we proved the biosemimetal or biofermion state and the topological character without referring to any theory. Any theoretical band calculation. So then so what is after biosemimetal? There is another topological semimetal that is possible in 3D. That's a nodal line. Murakami and Markov already talked about it earlier. Now there's a topological invariant you can define. And if you have particle host symmetry, you'll get the drumhead states. If you do not have that, then you will not get the drumhead state. You will get surface state, which is also interesting. But then many people predicted many things, but nothing happened. No experimental realization happened until we applied our intuition and our idea. And this is our theoretical prediction that this compound will be the one where to find it. And of course, we found it there because we know from experiments that it should be there, right? But this compound is interesting. Additionally, we're lucky that it's also superconducting. So it has this nodal line construction, but the surface states are actually above the Fermi level. So I'm out of time, so I'll get to the conclusion that this nodal line states can have induced proximity superconductivity. And then all these materials show chiral anomaly, all sorts of exotic physics, and that's what we are trying to probe now. So I would conclude by saying that the Weyl and nodal line, these two topological semimetals we discovered recently, both theoretically and experimentally, are the native zoo in the Venus matter physics. I mean, animals in the zoo. Thank you.
Questions and comments? Please try and go to the microphone. Well, I guess everything is very clear.
Okay, thank you.